TXY and PXY diagrams are very useful for presenting either calculated or experimentally measured liquid-vapor equilibrium data. Before we get into the charts, let's go over real quick again what the bubble and the dew curve are, or the bubble point and the dew point are. The bubble point, or curve, depending on if you want to keep a concentration fixed or change it, is where we have all liquid, and we are witnessing the first bubble of vapor being formed. Now conversely, the dew point is where we have all vapor, and we are going to change the temperature and pressure, and we get the first droplet formed. The two-phase region, also the liquid-vapor equilibrium region, this is where we have both liquid and vapor coexisting simultaneously. So jumping into it, if we look here at a TXY diagram, we'll notice two distinct curves. Before we get into the curves, let's do a really quick general overview analysis of this figure. On the y-axis, we see we have the temperature plotted. So in this case, in the TXY diagram, the temperature is variable and the pressure is fixed. So typically it'll say P equals something, for example. This is just a representative TXY diagram, but the pressure for this chart will typically be fixed. More often than not, it'll be atmospheric pressure. Down here on the x-axis, this is the composition. Z, I typically write TXY and PXY diagrams as a function of Z, which is the total composition of the system, the total molar composition. Component A is more volatile. So it is the component that is more likely to vaporize. And the reason why we do that is just to standardize the way that the drawings are made. So if we look at this figure here, if we have high temperature, regardless of the pressure, this is where we're going to have all vapor phase. So everything above this red line is going to be all vapor, regardless of the composition, so long as we're above this line. Likewise, at low temperatures, this will be all liquid. So if we have a mixture that is all liquid, and we begin to heat it up, the first thing that's going to happen is it's going to start to boil a little bit, and this will be called the bubble point. Likewise, this curve is the bubble curve. Conversely, if we come down from an all vapor point, this here is going to be the dew point, and likewise this is the dew curve. So what this chart basically shows is that for any composition, so if we have an overall mixture composition of, let's say, 30% A and then 70% B, and we would heat it up, this would tell us what the bubble point and the dew point were of the mixture. So at any temperature in between these two marks, you would have a mixture of liquid and vapor. So this is the two-phase region in between the dew and the bubble curve. Now this chart also shows us a lot more information than just the dew and the bubble curve. So if we were at this point right here, the bubble point, we would trace a horizontal line, and that would give us the composition of the vapor phase. So at a intersection between temperature and composition, that fixes the point and the state in our system. So that's where we can read the two different things. So going down here, this would be y of A, and this is x of A. If we were to choose a different point, let's say a 40% total composition, and actually let's change the color to make that a little more clear. If we had a 40% total composition at a temperature of 90 degrees, that would mean we would exist in the two-phase region. So at the intersection of these two lines, we could trace over and intersect the dew curve and the bubble curve. This would give us XA, the vapor composition, and this down here would give us YA, the vapor composition. The difference, the distance between these two curves and the relative point tells us how much of the physical phase we have. So in this case here, the 1 over the length of the line segment gives us the total amount of vapor. Likewise over here, 1 over the line segment length is the total amount of liquid. Now mathematically we can figure out how much total liquid and how much total vapor there are using the lever rule. But let's go back and look at this orange system here. So if we're taking a 0.3 mole fraction mixture and we heat it up to its bubble point, we can read the composition of the liquid phase, which actually matches the overall composition Z, and we can read the composition of the vapor phase, which is going to be enriched in component A because it's the more volatile of the species involved. And if we apply what we learned in the lever rule, we'll see that the dot is basically right on top of the bubble curve and very, very far away from the dew curve. That's because we have effectively 100% liquid in the system. Now conversely, if we were to go to a different system, let's say 90% A, and at the dew curve, we could read off the composition of XA, and we would see that we'd have 100% vapor over here because we would have the system conditions basically falling exactly on the dew curve. So we'll look at this a different way, going through an example. Let's start off with a 50-50 mixture of A and B, and we'll start to heat it up. So as we heat it up, we're still liquid, and we remain liquid until the point where we hit the bubble curve. This is where we form our first droplet, and that would be at a composition here given by YA that we would trace back down to the x-axis. If we continued to heat it, we would fall into the two-phase region. So let's say we heated it up to 86 in this case. We would have a total quantity of liquid, and we would have a quantity of vapor given by these different conditions here. And you can see as we put more and more energy into the system, we're creating more of a vapor phase. But due to the lever rule, we see that we have a shorter segment here and a longer segment here, which means that we have mostly liquid, right? You can think of it sort of as a tug of war where we have more liquid molecules pulling this little dot closer over here and fewer gas molecules pulling it over that way. If we continue to heat it up, and let's say we now heat it up to 90 degrees, the tables have turned where we have, in this case, much more vapor, we can tell by the shortness of the position here, and a lot less liquid. But we can still read off the liquid concentration of A and the vapor composition of A. And eventually, if we continue to heat the system, we will reach the the dew curve, or the dew point, in which case we will have 100% or nearly 100% vapor and a very small fraction of liquid, but we can still read what that liquid concentration would be. And we can see that since we have mostly vapor, right, the vapor has won sort of the tug of war, and the system conditions are basically the same as the vapor conditions. That means our total composition here matches our vapor composition YA. And that's the opposite case from when we started, where the liquid composition matched the total composition. So moving on, if we look at a PXY diagram, now a PXY diagram is effectively the same information as a TXY, but presented in a slightly different way. In this case here, the T is equal to a constant value. The temperature is going to be fixed, but we're changing the pressure. So let's say, for example, if this were at 50 degrees C, for example, we could still cause the phase change between liquid and vapor to occur by raising or lowering the pressure instead. But the same rules apply. The only difference is it's basically kind of flipped upside down. So at high pressure, it makes sense that everything is going to be in the liquid phase, whereas low pressure, everything is going to be in the vapor phase. So if we start off with a 50-50 mixture and we start to lower its pressure, Like imagine you're pulling a vacuum on a sample of liquid. This point right here, the first thing that's going to happen is you're going to have a droplet form. So this is going to be the bubble point. And if we keep on depressurizing until there's no more liquid left, we have the dew point. So likewise, we can call this the bubble curve and the dew curve. And then inside this region, we have liquid and vapor. But the same basic strategy applies to look at the PXY diagram as it does the TXY diagram. So let's say, for example, we had a system that consisted of 70% total composition at a temperature or pressure of 100 kilopascals. That would put us in the two-phase region. And from this, we could read out the composition of the liquid and vapor phases. So right here, this would give us X of A and over here, this would give us Y of A. Now, for a quick consistency check, this makes sense because A, recall, is the more volatile component. So it's the one that wants to vaporize in this particular binary mixture of A and B. So that makes sense then that you should have more of A in the vapor phase than you do in the liquid phase because it's the one that wants to evaporate. By the lever rule, we can see that this distance here is quite long and this one is quite short. So in the condition of 100 kilopascals and 70% A total composition, we can see that it is mostly vapor because that vapor has more material and sort of tugs and pulls that dot closer according to the lever rule. Now lastly, what we've looked at have been ideal plots. But that's not to say that liquid-vapor equilibrium can't get quite complex. So here's an example of a mixture of ethyl acetate and benzene. We can see that the behavior looks significantly different. This is a TXY diagram, which means the pressure is going to be fixed and we are changing the temperature. But let's take a look at it and see if we can understand the system, although it looks quite a bit different. Regardless of the composition, at very high temperature, we see that we are going to have all vapor. At very low temperatures, it makes sense that we will have all liquids. So that would tell us that going from the vapor to the liquid, this gives us the dew curve or the dew point. And likewise, if we were to go the opposite way, this gives us the bubble curve or the bubble point. And then inside this strange looking envelope, we have the liquid vapor equilibrium region. Now, one other point to mention in the TXY and PXY diagrams. At this point over here, we have pure component B, so that XB is equal to 1, XA is equal to 0. So this point right here, you'll notice that there is no transition between the liquid and vapor equilibrium region when we have a pure component. And that's because there is no two-phase region. The two-phase region only exists at a fixed temperature, and this will be the saturation temperature, which corresponds to the vapor pressure under that condition. Likewise, over here, we have XA is equal to 1, so we have pure A, and XB is equal to 0. We have no component B. And we can see over here that the Tsat for B is lower than the Tsat for A, and that makes sense because we have a more volatile species for A. But we can't have a region where we have liquid and vapor of only pure A at temperature other than its saturation temperature. So liquid vapor equilibrium systems can behave somewhat strangely, where you can have both a liquid and a vapor over a range of different temperatures or a range of different pressures. And that's what makes multi-component liquid vapor equilibrium distinct from single component systems. But the TXY and the PXY diagrams, although they can be somewhat complex for a non-ideal system, they're useful for material balances because we can simply read off what is the composition of the liquid and what is the composition of the vapor phase to then implement into any sort of a material balance that you may be working with.